Hey everyone. Today's video is going to be a bit interesting. So one of my favorite 3DO games is Killing Time. It's a very nostalgic game for me. And I've always wanted to try and recreate the vibe of Killing Time in terms of the environments and the type of environments that existed in that game. And so I recently undertook a project here to create my own 3D engine for the 3DO to mimic the style of Killing Time, and that's what you're looking at here on the screen. Well, you're looking at a prototype of that, an early prototype of that. And before I started this, what really gave me the idea is I was talking to someone on our Discord, on the 3DO community Discord, and we were talking about Killing Time, and I was wondering what type of engine they used, and he had mentioned that they had used WAD files. Well, WAD files are, of course, what was used to create Doom. And so I started looking at a lot of the geometry in Killing Time and comparing that to what the Doom level editors are capable of creating, and I can see the resemblance or the influence. So I started researching the WAD file format, and I started playing around with this editor here, which is Ultimate Doom Builder, and learned enough to create some simple sectors. A sector is basically an enclosed area within this the Doom Builder, or in the WAD data itself, that describes an enclosed area of line definitions. And the way to tell from one sector to the next is when you notice floor heights changing, ceiling heights changing, or the way that light, the static light changes. That's one way you could tell one sector from another. But in this map here, you're looking at Ultimate Doom Builder, and this is the data that is being rendered in the 3DO here. And so if we go back to the editor, you'll see this is basically the same thing. So I've recreated this using WAD data on the 3DO, but there's a slight catch, and that is when Doom was created, they were rendering everything per pixel. And this gave them a lot of flexibility in terms of different shapes that they could have. The shapes, the polygonal shapes of their sectors, and the various things that they were able to accomplish. A lot of control. Well, on the 3DO, I am using quads, and so I'm trying to figure out, based on a given sector, how do I dice this up? Now this does support. I made it support diagonal walls. So if I come in here and I do something like this, right? Actually, let me do something a little different. Let me make it an extreme diagonal here. And let me save that. Let me rerun my Python script to convert that data. That will work if I'm in the right directory. So this script, this Python script that I just wrote, it will go through the WAD data and it'll parse out what I need for my engine, which in theory is how they made Killing Time, rather how they got the data in their engine. But now that we have that, let me close this down. Rerun my compilation process here. I might be going off on a tangent here, but I wanted to show you this. Okay. So there is the diagonal wall that I just created. Okay. And you'll notice that even though the wall is diagonal, I still have to be tricky with the floor. So I'm going to leave this map here, and you're going to see what I did. So you see that? So I still have quads for the floor and the ceiling. But when my floors and ceilings are built, they are figuring out where to be placed based off of the outline of the sectors. So it's not going to create any more quads than it needs to. I suspect this is how killing time actually works. I'm curious, but if somebody loads up killing time in an emulator and they're able to use an editor, a hex editor or something to go in and alter things at runtime, if they were to make one of the walls disappear perhaps in a corner that has a diagonal, you're probably going to see something like that. I'm betting, but maybe. But you're looking at backface calling. That's why these walls are disappearing. So that's behaving the way it should. Now I've supported quite a few things from the WAD data. If I go back in, just to show you this really quick, and I come here and I maybe grab this area. Let me zoom in here and let me bring this up. And let me bring this down a bit. And let me grab maybe that texture and put it up here. It's not gonna, I can't do that. I need more textures. So this isn't gonna look right, but I'll throw that up there. All right. Down here at the bottom. Okay. And now let me save this, run my converter again, and fire up my engine again. So you can create some pretty interesting environments with this. I have some restrictions because I'm trying to use quads for everything. So it's a bit more cubical, but I still think it can look pretty good. So there it is. The wall textures for those faces don't look very good because I didn't have anything else at the moment. But yeah, it's pretty cool stuff. Now I'm really happy about the performance of this. So right now I'm forcing a weight on vPlank just so that it can control the movement a little bit better as I'm going through testing things. But if I remove that, you'll see how fast this is running, at least on the emulator. Let me disable this. Run this again. And if you look back here, you'll see the frame rate. So right now, this point of view, is running at 97. It's rendering 66 quads. These black lines that you're seeing, if that's even coming out, is it's because I'm using the sport to clear the background. That way, when I leave the map, it clears everything. Otherwise, it'll just keep drawing on top of itself. And it's just running so fast that it's not synchronized. The sport call is asynchronous. And it just the slower your program is running, you won't really notice this. But if you're running fast, you will. But let's talk about that. Like how did I get this to run this fast? So right now this is running at 143, 142. This angle here is at 110, 105. I get closer here. That's already jumping up to 174, 177. And I have a fall off there. You see that I'm leaving the frustum, so I'm calling it this entire view here, 77. It's still not bad, 79. But this is actually the second time I wrote this prototype in a week. The first time that I wrote this prototype, I was exporting out a set of all of the vertices for each quad, loading those vertices up into each of my quad data structures, and then based on calling information, I was actually, you know what? It'll be easier if I just do this. So the initial version was first I exported out all the vertices, and I built up my quad data structures instances with all those vertices. So I had a bunch of quads, and for each quad, I would first try and do a quick backface calling check. So really quick, if you have just let's just say a wall quad, and let's say that the normal is pointing out this way, and the camera is over on this side, for example, then you shouldn't see this quad. You're looking at the back, and in my engine, I'm not supporting that. So that's why these walls to the left and right are disappearing, because the camera is behind them. As soon as I come in, you will see them. Now the great thing is that the normals are only calculated once when the data is loaded. So that's kind of a free thing. It's not impacting performance. But after the quads were called, for everything that was left, I would then try and call it from the frustum. So if you can imagine a camera, if you're looking at it from the top down, and you have your eye here. I'm a terrible artist. You have your eye here. You're looking from the top down. Is a point inside or outside of this frustum? And I actually came up with I didn't invent it, but I have a pretty cool solution to this, which I'll share in a moment. But after the quads were called from this step, then I finally had a list of quads. Let's just say they're right here. And then I would go through each one of these quads. I would issue one call in the Mathfolio library to convert all these world coordinates to camera space, to camera coordinates. So if I had 50 quads in the rendering queue, I would have to call that 50 times, and I would pass in 4 vertices at a time. And it wasn't really working. I mean, it wasn't slow, but larger areas, you could notice that it was dropping, to 40 frames per second, bordering 30. And so I wanted to make this run quicker. And the secret of that success, knock on wood, is I decided instead to store all the vertices as a unique table in a linear set, and then have all of the quads reference those vertices in that table. So for example, instead of a quad holding coordinates, a quad holds indexes into a table. That table has coordinates, distinct coordinates. There's a caveat to that, but I'll get to that in a second. So I rewrote the converter. I rewrote the engine, the prototype of it anyway. And so now what I have is, you can imagine a table in memory of XYZ coordinates that I'm grabbing from the WAD file. Okay. And I have a table like this for every sector that I loaded in. And for every sector that I'm going to process in a scene, this is what I'm now doing. I have the table of XYZ values. And no matter what's going to be drawn, I process this entire set with one call to the Mathfolio to convert all of these vertices to camera space. So there is this function here, mul many vec4 by a matrix 4x4. So I have a view matrix that represents the camera, and then I have this long table of vertices that I've acquired from the WAD file, and I call this a single time. I pass in the number of vertices to calculate, which is the size of the table, basically, divided by 3. And then it will go ahead and it will do all of this in one shot. And this runs very quickly. It's kind of funny because later on I thought there was a bottleneck with this still, but there wasn't. I'll show you what that was. And I was able to fix that. But so no matter what, this runs. And now I go and see, okay, what needs to be drawn? But the nice thing is that regardless, I don't have to keep going back and calculating anything individually. Now, maybe I'm going to find this is going to cause a problem later on. Maybe, perhaps, if the sector is large enough. I'm not quite sure yet. But for the moment, this version is working pretty well. So with this new version, first I just process all those vertices with one call. Then I do my back face calling checks that I just explained before. All right, you got your camera looking this way, so this would get called. I got my frustum check, and then if it passes the frustum check, it goes on to be rendered onto the screen. That's the high level pipeline. Now, the frustum calling, that was a bit tricky too, because that could run very slowly depending on how you do it. Well, I'm using an old school method, which works pretty well in my opinion. And I can highlight that really quick for anyone interested. But imagine you are looking from the top down into a viewing frustum that the camera is making, right? And so something like this. And the camera is back here. There's my terrible eye, because I'm a terrible artist. Looking this way, so we're looking from the top down. And so the challenge is, well, is a point inside or outside? And so what I'm doing, let me go to the code here. It's right here. So what I am doing is I'm using similar triangles to figure this out. And I'm doing it with very simple math operations, which is the great part and why this is able to run so fast. So if you notice, you have, well, let me do this. So you can imagine this is your screen width. So this right here is your the near plane of the camera. This is the far plane. These checks are simple, right? If it's beyond this or hasn't reached this point, then it gets called. The tricky part is this angle part. And by the way, the way this works can work is when I do my camera transformations, I'm performing an inverse operation on the entire area that I'm transforming. So, for example, if the camera is moving forward, right, the world's moving toward the camera. If you're turning right, everything is rotating left. And so by taking the inverse, you end up with data such that you can treat the camera as if it's at world 000 looking down the positive z-axis. And it simplifies a lot of math. But that's actually critical to this solution. So you have these points, and what you can do is you have a view distance here. This is my view distance, which you can change to change the perspective a little bit. I made it a power of 2 value so I can do some tricks, but you have your view distance here. Well, what you end up having is similar triangles. You got one here, and you got one here. So what this ends up becoming is, sorry if this is getting very technical, but I found it interesting. If you have 1/2 of your screen width over your view distance, well, that's proportional. That's going to be proportional to the x that you're trying to find. This right here over z of the z-axis of this point right here. And so by doing a little bit of algebra, you can figure out this here, and then that will tell you what this point is for every z, right, within the frustum. And it will also tell you what this point is. This is a minus that extents, and this is positive the extents. So if the point you're trying to check is a little further back, it's the same formula, but now you're looking at something like this. And this would be your minus extents, and this would be your positive extents. So just with a little bit of algebra, you can call the frustum. If you look at my frustum calling, now there is a caveat here. In order to do this, I need to get the center of my quad, which is pre-calculated, and then transform that into camera space. I can probably change this later, but it doesn't seem to be impacting performance right now. And once I have that, I use that center point with a radius that I also pre-calculate. Really quick, that means that if this is my quad, I pre-calculate the radius, I pre-calculate this distance all around. So, if it's beyond the far, I junk it. If it's too close, I junk it. And then here's the x-axis extends check and the vertical one. Now, originally, this is what the x looked like. Multiplying this is basically the algebra part of this that I just described. But I was multiplying the z-axis by half the screen width, and then multiplying it by the inverse of my view distance, just so I can avoid a divide. And these multiplication calls, they can be expensive if you call them multiple times, because it accounts for 64-bit data. Well, sometimes you don't need that, right? And it can be expensive. But the trick that I did for this was using power of twos. So, for example, the half of my screen width was not a power of 2, but I was able to get there by partitioning up this this math here. So, for example, taking the z-axis, shifting it over by 7, then adding it to the z-axis shifted over by 5, and then shifted to the right by 8, I basically accomplished the exact same thing up here. This part effectively did the multiplication of that I needed up here. And then this shift was the same thing as dividing by the power of 2 representation of the viewing distance. So it looks very cryptic, and this is when I feel like you definitely need to comment what you're doing when you have stuff like this. But I mean, this is great. I mean, I turned this into bit shifting, and that really sped up my frustum calling. And so once I have that extends value, which is right here or here, all I need to do now is just check the radius with the center point of that quad. If it's less than minus extents, or if it's greater than the extents, then I call it. That means it's too far to the left or too far to the right. And the y-axis is very similar. The only difference is the formula is changing with the screen height, half screen height. And then I can check the y extents. Anyway, but it's pretty cool that I was able to get this to run using just very simple shifting operations, and it works pretty well. So the next thing to tackle was I noticed that the 2D projection part was taking a long time. So if we go to, I'll give you a tour of the code here in a second also, if you're interested in that. But this is the meat and potatoes of everything. So when a sector is converted to the screen, what I'm doing is I'm checking to see if it's a vertical quad, because vertical quads need to be clipped to the camera. If your data is going behind the camera and you're trying to do a 3D projection, then hilarity will ensue. To show you what exactly this part of the code is doing, let me fire up the demo again. Okay. So yeah, let me turn that sync back on so we don't get those black lines. I also incorporated the light levels, so you can make certain sectors bright, certain sectors dark, and you can create some pretty interesting effects that way. I also want to support the lighting that Killing Time used, which was that fall-off lighting, but I want both. So right here, for example, I am in the wall right now, and I am moving into it, right? It's clipping it to the camera. If I were to get close to a wall like this, same deal. It's clipping it. If I wasn't clipping it, you would see geometry just kind of going everywhere. Even when you turn like this, right? It's clipping it. And so, let me go back there really quick. So if it's a vertical, then I know I need to clip it. I have some wiggle room with the floors and ceilings, and I can show that in a bit, but I can just clamp that to the near plane, and you can't really notice it, that's happening, but you can't really do that to the walls because it won't look right. This looks complex, but basically what it's doing, if you have some quad like this, I'm going to try my best to make it look like it has perspective. And it's cutting into the near plane, the camera, like this. Well, you have to find this point, or this one, the intersection, and then you clamp it, you clip it, or cut it, whatever terminology you want to use. Basically, this part is gone, right? This becomes your new quad right here. And so that's what this is doing. One of these will check going one way, the other checks the other way, and it just clips to the camera. And then down here, this is where it does its 2D projection. And this is where I also saved I saved about 12 to 13 milliseconds per frame, which doesn't sound like a lot, but it adds up. And what I was doing before was using this multiplication again, this small SF16, which can account for 64-bit, I believe. And really quick, in a nutshell, if you have some XYZ point and you're trying to figure out the 2D projection of it using sort of old school methods, you could do you would do X, right? X times some view distance, which is something you can configure yourself and change and see the effects, divided by Z, and then you would do Y times that view distance as well, divided by Z. And then just because of the way the math works, you also have to add half the screen width and then half the screen height, and you get your 2D point. So it's not very difficult. So that's what this multiplication was doing. Now I was doing a shift to avoid another multiplication, and I'm doing a multiplication on an inverse of a Z lookup table to avoid a division, but it was still running pretty slow. And I realized that because all the data rotates around the frustum, at this point, if I'm dealing with some data in the frustum, I can predict how large that data is going to be, and that data is not large enough to overflow. So I was able to remove these multiplication calls from the math library and just do a straight multiplication. So I shift my fixed point down, do the multiplication, which brings it back up, and this, believe it or not, was a huge gain right there. But with all that cool stuff said, let me just show you high level of what I got going on here. So I have some flags for my quads to call them or to draw them fast. And what that means is if you go back to what we were just looking at, you'll see fast map cell here and just map cell. So these map cell functions, they're taking points, 4 points, and they are changing the vectors of a cell to give it perspective. So after I calculate all the screen points, I then use this to map those points onto a quad. Well, when you're dealing with cells that are the sizes of powers of 2, you could use fast map cell, and this works a lot quicker, as the name suggests. If you're not dealing with powers of 2, then you would use something like map cell. And so the reason why I have a check for both is because my walls in my demo there are pretty tall. They're not the same size as other walls would normally be, which are going to be 64 by 64 units. Those tall walls are more like 64 by 192 or something like that. Now, fast map cell actually still will render it, but it will look horrible. So for any wall that's kind of abnormal, every now and then maybe you have a high ceiling and you want to use a tall wall instead of stacked 2 64 by 64 unit grids, then I can use fast map cell or map cell. But anyway, some of the data structures that I got, light level, 3D space. Here's my quad. So these are those this is the lookup table that points to the vertex table. The center, this is going to calculate where the screen points are, the cell, the normal, the radius is pre-calculated, the normal is pre-calculated. And some flags, a type, so is it a horizontal or vertical? If it's horizontal, it's going to be basically like a ceiling or a floor, or something that looks like a floor, a flat, basically. A vertical is always going to be like a wall, something I'm going to have to clip. And I have the sector, which has like the light level, how many quads are in there, the quads, the floor height, the ceiling height, the floor and ceiling textures, the world vertices, and then the camera vertices. So when I call that multiply vector by many by the matrix, then the camera transformations are going to be deposited into camera vertices. A map. So what I'm thinking of doing is, in Killing Time, if you've played it, as you're running around the world, you're always in a zone, an area. And if you were to bring up the in-game map, you would see like the percentage of completion of that area of exploration. In my engine, I'm going to call that entire zone a map. And the map is going to have sectors. And a tricky thing is going to be the space partitioning, which is probably going to be very challenging. But once I have space partitioning, it should be able to have many sectors in it and not really matter. But so map is going to have sectors. Sectors have the quads. And then I got my camera. I have lookup tables. View matrix. This is something that runs every frame, and it uses the camera's position and the camera's rotation to create a single matrix. And this is the matrix that ends up converting all the world coordinates to camera coordinates. And let's see. So the main loop, update scene, which will update the view matrix, update the vertices for the sectors that are being processed, call what's in the sectors, and then create the screen coordinates. So update scene, and then if we have anything to render, it will link all the cells together and then draw them. There was something weird I ran into with this. So this just loops through and prepares a list of cells to render. I tried building this list as items were being added, and for the life of me, I couldn't find any bug whatsoever, but it was glitching out, and I think maybe it just has something to do with the compiler, or I was trampling memory. I have no idea. I have to go back and look at that. But so for now, that's a separate step, but it doesn't seem to be causing any performance issues. I wrote a very simple profiler. Here it is, very simple profiler, so that I can check how long it takes for things to run. And I was in here earlier testing all sorts of things. And that's the main loop. So, I mean, the meat and potatoes of this is the calling, the transformation of data, converting the data to the screen, and then of course my conversion script to take the WAD file and produce something that the engine can use. So a tricky thing is going to be the space partitioning part. So if a map can have, let's just say 50 to 100 sectors, I mean, if you have 5 steps, that's technically 5 sectors because they have different floor heights. Then, how do I only process what I need to process? And so I know Doom used a binary space partitioning tree, a BSP tree. I don't think Killing Time used it. And the reason why I say that is because if you notice, the doors in Killing Time for 3DO, they rotate when they open. And that's a little suspicious to me because I created a BSP tree once as a test some time ago. And I know that if you, and correct me if I'm wrong here, if maybe I just didn't create a BSP tree fancy enough, but if you rotate your geometry, your tree is now void, at least a part of it is, and you have to recalculate things, which probably isn't something you want to do in runtime for a game on old hardware. So if you notice in Doom, the doors all open vertically. And so if your line segments are going up and down on the y-axis, then that doesn't change your geometry. It's still, the line is the same. It's just in a different, it just have moved up or down, but it hasn't rotated. So whatever was in front of that line and behind that line prior is still true after it goes up and down. But if you rotate your geometry, that all breaks. And so, fun fact, actually, I just finished playing the PC version of Killing Time, which I also loved. I played that for the first time. I'm late. And I noticed that all those doors open up and down. There's some static doors that look like they're swung open, but they actually don't move. And so I have a feeling the PC version used a BSP tree and the 3DO version did not. Now, what would be nice is, see, if you were rendering this scene right here by pixel, and if you had a BSP tree, you could render from front to back. You could check, you can traverse your tree in such a way where as you're plotting your points, once every point has been plotted, you stop because you know that your view has filled up, and so you're not doing any overdraw. Well, I can't really do that with this because, I mean, again, correct me if you have an idea, but since I'm drawing quads, it might be pretty difficult to try and figure out, based on quads that are being drawn, if all space has been filled, or how resource intensive something like that would be. So I suspect that the way Killing Time is working, and if there's like an old Killing Time dev watching this video, please let me know because I love this stuff. But I have a feeling it's got some algorithm to traverse and figure out nearby sectors. And then it draws them in a painter's algorithm. And that's probably why the performance is what it is. Well, who knows? But it's probably doing a painter's algorithm type thing. But anyway, I still have to think a bit about how to do the space partitioning. But before I do that, I want to finish making sure that I can render the sectors properly. I still have to support when like the ceiling is sunken in and the floor is sunken down. I'm also not doing any sorting right now. So depending on the way the sectors are built, it may not render properly. One thing that's really cool that I added, I mentioned it briefly, are light levels. So let me just remove this stuff so it goes back to what I had. Okay, so if I come in here and I make this darker, wait, no, not that. I want, excuse me. I want this. I'm gonna make it real dark. All right. And this is gonna look really bad, but I'm gonna leave this sector where it is, so it's gonna be lit up. See what that looks like. So this has a brightness of 2. This has a brightness of 0. Currently, my engine supports 8 different brightnesses. 3 would be standard, and then it can it could be brighter from there or darker. But let me run my script again. And by the way, I just want to mention the only reason why I'm using killing time textures here, I'm just trying to get a feel for, does my engine look like killing time? I'm not trying to rip off killing time. I'm not going to, if I make a actual game out of this engine, which I do plan to do at some point, I'm not going to be creating anything to do with killing time. This is just something that I'm testing. But now you can see how dark the room is. And that pillar just stayed lit because I didn't change it. But I'm thinking what I can do is have 2 modes of light. So I have the light levels, where you can design a room in such a way to make it look like it's lit up, or some areas are darker. And then I can have another light feature that's like killing time, where the farther something is, the darker it gets. And I'll have to use a real cheap algorithm for something like that, because I wouldn't want that to impact performance. So it would probably be something like calculating like a quote unquote as the crow flies distance, not an accurate distance. And then just based off that, look up a table of a light value. And so, like diagonal, like quads that are diagonal from you might not be illuminated the same as quads that are, right next to you, perpendicular to you. But that's okay. I mean, that's how I noticed killing time works anyway. So they're probably doing something similar. But anyway, I will keep you guys posted. I hope you enjoyed this. I'm really excited about this. It's quite a leap from BioFury to go from BioFury to something like this. But this gives me a lot of nostalgia. I love it. And Killing Time was one of my favorite games. So it's really cool to see something old be revitalized in this way, and to see an engine that is taking shape to create something that you used to love, as a young adult or younger. So yeah, I hope you enjoyed this, and there will be more to come. Thank you.